Okay, the goal for today is to finish all the material for this course. We'll see if that happens. And then, as I said, next week will be a review. So before I get into that, just a couple of last reminders. So tomorrow, Friday at 2 p.m. in SEC 102 is our exam review for midterm 3. And then for the final exam review, it'll be next week, both in class and Friday. So it'll be 34 questions, just like the real final. So I'll post all of that together, probably today or tomorrow. And then once we go through it, I'll also have in Blackboard information about how they're going to be divided up. So we're going to divide it into 3 parts, as I said. So it'll say in Blackboard which questions we're going to cover on which day, so you'll be clear on that. At least that'll be what the plan is going into it. And then I'll post the videos and the completed notes sort of piece by piece as we finish them. So they'll kind of come in parts. So that's how it'll be. So just have to check Blackboard to get details on how that's divided up. I haven't exactly decided yet, but it'll roughly be a third of the review each time. Tuesday, Thursday, and then Friday for the review session. All right, so that's what's coming up. Also, my regular plug for course evaluations, which are available online until May 2nd, so please complete those if you haven't done so. All right, so we're going to just finish, we're going to start today by just reviewing what we learned last time a little bit, which are the structures of metallic solids. So we talked about 4 structure types. The 3 that you should definitely know the most about are the cubic ones. They're the most easy to visualize and things like that. But we also talked a little bit about hexagonal. So what we really need to know are a few key aspects of these structures. So we went through a lot of details last time to sort of help you understand them, help you understand where some of these numbers come from. I mean, at the very minimum, just know the information in this table, you'll be in pretty good shape. There could be some questions that extend beyond this sort of knowledge-based material, but at the same time, if you know the information that I'm going to put in this table here, that's kind of the essential elements that you'll need for this part of the course. So the first one I talked about is called primitive cubic, or simple cubic. So we call it a simple cubic, and the other name for it is primitive cubic. So some of these have more than one name that you should be aware of. So simple cubic or primitive cubic mean the same thing. And as we said, this is the simplest one where you just have one atom on the corner of each of the 8 corners of the cubic unit cell. So the way that we would count that then is we have 8 corners occupied. Each atom counts as 1/8. And so in total, there's 1 atom per unit cell in a simple cubic structure. The coordination number we defined at the end was sort of the number of nearest neighbors that each atom has, the number of atoms that it's touching in that structure, if you want to think about it that way, and that was 6 for simple cubic. So there was the 4 in the same layer as it, and then 1 above, 1 below. And the other thing that we defined was packing efficiency. So you don't necessarily need to memorize the exact numbers, though it is helpful to know them a little bit. But for simple cubic, this is the least efficient packing, meaning it has the most empty space out of all these different structures that we talked about. It was 52.4%, meaning that's the percentage of the volume that is occupied by the atoms in the structure, the rest being open space. The next one we talked about is called body-centered cubic, and it has an abbreviation that's pretty intuitive, BCC. So if you see that abbreviation, that's what we're referring to. And when we count the atoms per unit cell here, in all of these cubic structures, we have all 8 corners occupied. So that's the corner atoms, but then we also have one in the very center of the cubic unit cell that belongs entirely to that unit cell, so we count that as 1 total. So in that we have, I'll circle the numbers, that's actually the real number, 2 atoms per unit cell in body-centered cubic. The 8 corners plus the center adds up to 2. And the coordination number for this was larger, it was 8. And again, that's easily visualized by just looking at the atom in the center of the cube and knowing that it is going to be bounded by all 8 of the corner atoms that are surrounding it. So that's how you get a coordination number of 8. And the packing efficiency for this was higher because we're filling in a lot of that empty space with the extra atom in the center, and it came out to 68%. Okay, so that's body-centered cubic. Face-centered cubic is the one that we'll talk about the most today in the context of ionic structures. And face-centered cubic has a couple of different names. It can also be abbreviated as FCC for face-centered cubic, or you'll sometimes see it referred to as CCP, which is cubic closest packed, meaning it's the cubic structure that has the closest or most dense packing to the atoms. So when you see CCP or close packing, that refers to this structure here. In terms of the number of atoms per unit cell, again, all 8 corners are occupied. So you have 8 times 1/8 for the corners, but then we also have 6 faces that have an atom in the center of each face. Each face is shared by 2 unit cells, so that will count as 1/2 of an atom for that particular cell. And so it's going to be 6 faces, each counting as a half. So in total, that comes out to 4 atoms per unit cell for face-centered cubic. And then the coordination number for this one was a little bit harder to visualize because you had to think about the layers of atoms that make up the structure. It's not obvious from just looking at the cubic unit cell, but we got a coordination number of 12, and that's because you have 6 atoms in the same layer that would surround one, and then 3 above and 3 below that cap that atom. That would give you a total of 12 atoms surrounding it. And the packing efficiency for this, as we said, is the highest that you can possibly have for a cubic structure, 74%. All right, again, the relative ordering of the packing efficiency is the most important thing to know. The other one we talked about is hexagonal, which in a lot of ways is similar to face-centered cubic, but it's just a different way of building the layers. So face-centered cubic was an A-B-C stacking where we alternate 3 layers before repeating the pattern, and then hexagonal was an A-B stacking where we alternate 2 layers before repeating the pattern. So it's just a little bit different in how we stack them. In terms of counting the atoms per unit cell, it's not as straightforward for hexagonal, but just know that the number is 6 because the cell is not a cube anymore, so it's a little bit hard to visualize how the atoms are shared in this case. But total is 6, that's what you should be aware of. But the coordination number is the same as it is for face-centered cubic, as is the packing efficiency. All right, and so both of those have identical coordination numbers, identical packing efficiencies. They both have the same percentage of their volume occupied, that just the unit cell is shaped a little bit differently. All right, so any questions on that? Again, that's the essential information that you should take out of what we learned last time. All right, what I'll close with for metallic structures is an example problem. This is more complicated than anything we'll ask you to do on a test. Perhaps on the homework there'll be something like this, but not likely the exam. But if you can understand and follow what we're doing here, this kind of helps you understand these structure types a little bit better and also understand what we can do with them. Why is it important to know, the dimensions of the unit cell and which corners and which faces are occupied, all that stuff. So one thing you can do is you can calculate the density from the unit cell structure that you have. So if we have sodium, it's a sort of a soft metal shown here, but it crystallizes in a body-centered cubic structure, and the side length A, the length of each side on the cube, is 429 picometers. Pico is 10 to the minus 12. We want to calculate the density of sodium in grams per cubic centimeter. So just by knowing what type of structure it is, body-centered cubic, and just by knowing the size of the unit cell side length, how long each side is in the cube, you can calculate the density, and we'll see how to do that here. So the density is going to be defined, of course, as mass divided by volume. And so what we're going to do to figure out the density using this information is we need to find out in a single unit cell of this structure, 1 cubic cell, we need to figure out how many grams of sodium are in there. And then we also need to figure out the volume of that. And again, the units we want are centimeters cubed, so to make sure that we're putting that in the right unit, centimeters cubed. We're going to do this for 1 unit cell. All right, so to get the numerator, how much sodium is in the unit cell, what we have to remember is that based on the structure type that we have, we can count how many atoms are in there. So for body-centered cubic, as we just reviewed, there are 2 atoms per unit cell in total. So what we can do is figure out what's the mass of 2 sodium atoms that would be inside of this unit cell. So this is a conversion that goes back to stuff we did in chapter 5, mole conversions. So we have 2 atoms of sodium. We can convert to moles of sodium using Avogadro's number.
Well, how do we get 2 atoms?
So this is because it's a body-centered cubic structure. So whenever you have body-centered cubic, there's 2 atoms in the unit cell. So that's one of the parameters that differs between these different unit cell types, is how many atoms in total are in the cell. It's going to be 2 for this one, body-centered cubic. All right, and so we have 1, we're going to convert to moles using Avogadro's number. And then once we have moles of sodium, we can then use the atomic mass, which is 22.99 for sodium, straight off the periodic table, to get grams of sodium. So all we're doing here is figuring out what's the mass of 2 atoms of sodium, the 2 atoms that would be in that unit cell. So this, of course, is going to come out to a very tiny number because it's just a very tiny piece of sodium that we're talking about here, 1 unit cell. But it's 7.64 times 10 to the minus 23rd grams. Okay? And then so that's the mass. That's going to go in the numerator here. And then we have to figure out the volume of the unit cell as well. So as we talked about a little bit last time, and we should know from sort of just basic high school geometry, the volume of a cube is just the cube root, or sorry, the cube of the side length A, so A cubed. So the volume is A cubed, the side length cubed, and that's going to be 429 picometers. So it's going to be 7.90 times 10 to the 7th, but that's in cubic picometers, which is not the unit we want. We want cubic centimeters here. So then we have to do some conversions to get it into the right unit. So it's going to be just using our metric prefixes, really. All right, so a picometer is 10 to the minus 12. So 1 meter would have 10 to the 12th picometers. We're going to cube that because it's cubic picometers in this unit. And then we have to go to centimeters next, which is 100 centimeters in 1 meter. And we'll also have to cube that because, again, this is a cubed unit. All right, so that's just conversion. I did it in 2 steps because I don't know off the top of my head how to go from picometers to centimeters, but you can go picometers to meters, where pico means 10 to the 12th, and then centimeters is 100 per meter. So that's the way we did it, and we got just a different exponent, of course, when we do that, 7.90 times 10 to the minus 23rd cubic centimeters. So again, a very tiny volume, because we're just talking about 1 unit cell in the structure. So we're now ready to calculate density using those 2 numbers. We found that there were 7.64 times 10 to the minus 23rd grams. We found that the volume is 7.90 times 10 to the minus 23rd cubic centimeters, and that comes out to 0.967 grams per cubic centimeter. So this is the calculated density based on the structural information. And if I go to the most reliable source for scientific information in the world, Wikipedia, not really, but it works for most things. Wikipedia tells us that the density of sodium is 0.968, so basically identical to that. All right, so you can, of course, measure the density using typical methods, measure the mass, measure the volume, or you can calculate it from the crystal structure, and you see that they match up nicely. So the crystal structure does have that sort of relevance to some of the macroscopic properties. In this case, density is what we went through here. So again, this is more complicated than we would ask you to do on an exam, most likely. I don't want to promise for sure because I haven't gone through all the final exam questions yet, but nonetheless, if you can follow this and kind of at least know what we were doing, that helps you understand sort of what's going on here. All right, any questions on metallic structure types? All right, no? Okay, so what we're going to move on to next is a different type of solid. So again, the last half of this chapter 9 that we're covering deals with different types of solids. That's the last phase of matter that we haven't covered yet. And we're going to talk about one class that's called network solids. Now for these, we're not going to go into as much detail on the structures like we did for metals, but we're just going to learn a little bit about how they're classified, a little bit about their properties, and things of that sort. All right, so a definition of a network solid is it's an extended solid, so it has, you know, 3-dimensional infinite structure, just like we would in any crystal structure, but it's going to be formed by covalent bonds. All right, so we said that metallic structures are formed by metallic bonds, where you have the valence electrons of the metals sort of delocalized, and that sort of holds everything together. These are going to be formed by covalent bonds, and what you can think of them as, we talked about, you know, a lot in chapter 3 and 4, how a molecule is, you know, a small unit made up of covalent bonded atoms. You can think of a network solid as just like an infinite molecule. So, you know, it has that same covalent bonding, that localized covalent bonding that we talked about, or delocalized in some senses as well, depending on the context. But these are going to just be bonded in all directions forever. So it's not just a discrete single molecule, but it goes on forever and ever in all directions. So there's going to be a few different classifications within this. So we'll talk about first network atomic solids. So these are network solids that have just a single type of atom, and they're elements, in other words. And one element that is a great example of this is carbon, which actually has 2 forms that would be classified as network atomic solids, or network solids is the more simple name for that. So the first of these is diamond. And so this shows, we showed this picture earlier before, but this shows a little bit about just a small piece of the structure of diamond. But again, this goes on and on and on in all directions forever. It's not just this little, what does this have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This has like 14 atoms in it. It's not that diamond is 14 atoms. It goes on and on forever throughout the whole crystal that you have of that diamond. This is just a small piece of it. And the key thing here is that if we look at each carbon atom in this structure, let's focus on one here, it's bonded to 4 other carbon atoms. So as we learned back in chapters 3 and 4, this defines it as a tetrahedron. So each carbon atom has a tetrahedral structure. Let me spell that right. So it's made up of tetrahedra of carbon atoms. So each carbon atom in the structure is tetrahedral. And so as we know, if you have a tetrahedral carbon atom with 4 things bonded to it, that means it's sp3 hybridized. And because of this, it has all sigma bonds. So the only types of bonds that we have in diamond are sigma bonds. When you have sp3 hybridization, you can't have any pi bonding. So that's how diamond is bonded together. It's all carbon atoms, but they're all sp3 hybridized. But then the other major form of carbon, which is actually the most stable form, is in what exists, as the standard state of carbon, is called graphite. So in graphite here, what we have to sort of describe the structure, what you'll notice is we have these hexagons of carbon atoms. But again, they extend in all directions. They're 2-dimensional now. They're not 3-dimensional, but there's these 2-dimensional planes of carbon hexagons that just extend in all directions. So it's a big flat sheet. So they're hexagons of carbon atoms. You can almost think of it like a honeycomb in some sense. And they're stacked into layers. So you have these flat 2-dimensional sheets kind of shaped like honeycombs, and then they're going to be stacked on top of each other to make that 3rd dimension. And the difference here, if you'll notice, is that each carbon now is only bonded to 2 others, and that makes it, or I guess 3 others, one, so like this carbon here, let's focus on, has 1 nearest neighbor, 2 nearest neighbor, 3. So it's bonded to 3 other carbons, so that makes it sp2 hybridized. So again, that's the major difference between diamond and graphite. Diamond is sp3, graphite is sp2, and that means it has sigma and pi bonds. Because when you have sp2 hybridization, you're going to use the sp2 orbitals, 3 per atom, to make the sigma bonds, and then you have an unhybridized p orbital that's going to be able to overlap with other unhybridized p orbitals to form pi bonds. It's kind of like the benzene structure we talked about a while ago, where you have a perpendicular p orbital of each carbon, and that's what's shown in yellow here, and those perpendicular orbitals are able to do side-to-side overlap and make pi bonds with all the ones that are around them. All right, and so we're going to get into a little bit then about how this affects the properties of these two. They have different structures, different bondings. So how does that affect the properties? That's what's coming next. The other definition to be aware of at this point, just in case it comes up, is that when you have 2 forms of the same element, so these are both carbon, but 2 different forms of that, we call those allotropes. So allotropes are when we have 2 or more forms of the same element. And carbon is the most common element that you would see. Both these allotropes, of course, are very common and also have very important uses in different industrial or technological applications. All right, so that's going to be the structure and bonding in carbon. But then what's important to also think about is how does this different structure and bonding influence the properties of these? And so let's look at some of the differences in properties and talk about then how that relates to the bonding. So as we know, diamond is very hard. It's one of, if not the hardest substance that you can find on Earth. And we also know that it's colorless and it's an insulator. All right, so those are some of the key properties of diamonds: its mechanical properties, its color, and its sort of electrical properties. And then graphite, in a lot of senses, is opposite in a lot of ways. So graphite, if you've ever seen it, it's soft and slippery. So it's very easy to break graphite. If you had a piece of it in your hand, you could just break it like a cracker. It's not that hard at all. And it's black in color, as you probably know, so it's not colorless like diamond, and it's an electrical conductor, not an insulator, okay? And so what you basically have is, two different forms of carbon, and just by changing the bonding and the structure, we have huge differences in properties. And that's, to me, one of the most interesting things about chemistry is how you can, use the properties of the electrons to rationalize, vastly different properties in the structure. And so to help explain why this is, in particular to explain the electrical conductivity of these, we can look at what's called a band structure diagram. So a band diagram is kind of like a molecular orbital diagram for a solid. So we talked about molecular orbital diagrams in chapter 4 for diatomic molecules, two atoms bonded together, and you have bonding orbitals that go lower in energy, antibonding orbitals that go higher in energy. You can do the same thing for an extended structure, but this time you don't have just a few orbital levels that are sort of separated, but you have a lot of orbital levels that are close together. Because in an extended structure, you have a ton of atomic orbitals that can participate, and the bonding is often very delocalized in those structures. So you get a lot of molecular orbitals that are all really close to each other. Now, when you have an insulator like diamond, which is going to be true for most nonmetals, it's actually rare to have graphite being a conductor. Most nonmetals are not conductors, but graphite's a rare exception. Most nonmetals are insulators. And so what you have in those cases is a large gap between the filled and the unfilled molecular orbitals. So again, you don't have nice individual orbital levels like we do in a diatomic molecule, but you'll have these bands of orbitals that are all close together. So they're going to be indicated with these blocks. So basically this block here is just a whole bunch of orbitals really close together that kind of all smear together in almost a continuous set that are going to all be filled in the ground state. And then above that, with a pretty significant gap, you have the empty molecular orbitals. All right, and we have names for these in the context of band structure. So the one that's filled is called the valence band. And the one that's unfilled is called the conduction band. So those are terms you should know. And in an insulator, the key aspect of these is that you have a large gap between the valence band and the conduction band. Now for diamond, let's think about why that is. In diamond, we have all sigma bonding. And as we talked about in molecular orbital theory, when you have sigma bonds, you have a large splitting between the bonding and antibonding orbitals, because you have really strong directional overlap between the orbitals. That results in the bonding orbitals being stabilized by a lot, antibonding orbitals going up in energy by a lot, and there's a pretty significant gap between them. So this is what happens in diamond when you have all sigma bonds. You have a large gap between the sigma bonding orbitals that are filled and the sigma antibonding orbitals that are higher in energy and unfilled, and that leads to insulating properties. Because in order for the material to conduct electricity, electrons would have to hop from these filled orbitals to the empty orbitals as they move through the structure, and there's a large energy gap, so they can't do that very easily in an insulator. Now in a conductor, which is how most metals are going to behave, as well as graphite, the example we just gave. So pretty much all metals are conductors, and then we just talked about graphite being one, a rare example of a non-metal conductor. What happens in conductors is, as we talked about for graphite, it's a little bit different reason for metals versus graphite. But in graphite, the one we just talked about, now we have a bunch of pi orbitals involved because we have pi bonding between the carbon atoms. And as we mentioned in Chapter 4 as well, when you have pi overlap, it's a side-to-side overlap. It's not as strong of an overlap, and so the bonding and antibonding orbitals don't split as much in pi bonding. So what happens in graphite then, or in other conductors for different reasons, is that the filled molecular orbitals, the valence band, which is still called the same thing, and the empty molecular orbitals, which is still called the conduction band, those are going to be right on top of each other in a conductor. There's no gap between them. Okay? And again, for graphite, that's because you have the smaller splitting involving those pi orbitals that are filled, and then the pi antibonding orbitals that are going to be right above that and unfilled. So in this case, for conductors, you have no gap between valence and conduction band. And because there's no gap, it's very easy for the electrons to move through that, because, again, if an electron is going to move through the structure, it has to enter an empty orbital to move to a new place, and those empty orbitals are right on top of the filled orbitals, so there's no energy gap. They can just hop right through, going between filled and empty orbitals quite easily. So this is the key difference between an insulator and a conductor, and it's related to how far apart the molecular orbitals are that are filled versus those that are empty above it. And that's what kind of distinguishes them from each other. All right. Now, the other thing that we have that's sort of in between these two extremes are called semiconductors. So the classic example of a semiconductor is pretty much most of the metalloids. So we said that, you know, non-metals tend to be insulators, metals tend to be conductors. So if you're in the in-between region, of course, that would be metalloids, which are kind of in between metals and non-metals in the periodic table. So those are the ones that are right along that staircase, you know, between metals and non-metals that we talked about a long time ago. So example would be, the classic example would be silicon, and there's others like arsenic and I think antimony. Those ones that are sort of close to that staircase. Boron, I think, can be a semiconductor. So there are those metalloid elements that are kind of between metals and non-metals. Silicon is the most important one. So silicon, which is used as the solar cell absorber. So if anybody has solar cells in your house, those are made out of silicon, or sometimes what's called a doped silicon that we'll talk about. And that's a good semiconductor, which when it absorbs light, it allows those electrons to hop and move. So that's how solar cells work. But anyway, what you have in a semiconductor is a small gap between valence band and conduction band, or an intermediate gap. So they're not right on top of each other like they are in an insulator, but they're not too far apart like they are in, sorry, they're not right on top of each other like they are in a metal or a conductor, and they're not far apart like an insulator. So your valence band and conduction band are sort of close to each other, but there is a small gap. All right, so in a semiconductor, you have an intermediate band gap in between insulator and conductor. And one difference is that in metals, the conductivity actually increases if you lower the temperature. So if you want a metal to be more conductive, you have to lower the temperature, and that's because the atoms become more ordered, so it's easier for the electrons to hop around. For semiconductors, it's opposite though. In the semiconductors, the conductivity increases with temperature. So that's how you sort of distinguish a conductor from a semiconductor. And the reason for that is, again, you have a small gap that the electrons have to hop over to be able to conduct from the valence band to the conduction band. And if you give them more thermal energy, if you heat them up, they have more electrons have enough energy to make that hop. So as you heat up the solid, there's more electrons that can hop between the valence and conduction band, and that increases your conductivity. Again, this is an energy diagram here. All right, so that's how it works for semiconductors. Now, the other way you can make a semiconductor, so an element like silicon, and some of these other ones in certain forms, but silicon being the most important one, an element like silicon that's a semiconductor by itself is called an intrinsic semiconductor. Just silicon on its own can be a semiconductor, but you can also either make new semiconductors or you can sort of change some of the semiconducting properties by doing what's called doping. So there's two types of doping. What you do with doping is you just mix a little bit of another element with that other one, with the main sort of constituent element. So an example is N-type doping is when you dope with something that has extra electrons. So an example of N-type doping is what would be called arsenic-doped silicon. That's one example. So let's look at the periodic table at arsenic and silicon. And so when you have N-type doping, again, we're adding a little bit of extra valence electrons into the structure. And we're just doing a really small percentage. I mean, I think it's usually like 1% or less doping. It's not a large amount of that you need. But what you do is you would start with silicon. So silicon is over here in group 4, right underneath carbon. So silicon has 4 valence electrons. And for N-type doping, you're going to dope it with something that has more valence electrons than silicon. A classic one that they use, you need to have similar energy levels and things, is arsenic. So for arsenic-doped silicon, we replace a small percentage of the silicon atoms with arsenic, and that puts a little bit of extra valence electrons into the structure because arsenic has 5 valence electrons versus silicon, which has 4. So the result of that then is if you look at the band diagram for silicon, again, energy level diagram shown here, you have a valence band at the bottom that's going to be filled. And in regular silicon, you have, you know, some gap where you have your conduction band up higher.
Left side of the arrow.
Energy.
Oh.
So these, right, so these are energy level diagrams where the valence band is lower in energy and the conduction band is higher in energy, just like we have in a molecular orbital diagram. But when you have N-type doping, for example, arsenic doped silicon, you're adding some atoms to the structure that have more valence electrons, and you're putting some filled energy levels close to the conduction band. So in arsenic doped silicon, some of those extra valence electrons that you have from arsenic end up in energy levels that are close to the conduction band. And so now you have electrons that are close to the conduction band and can more easily move into that conduction band. All right, so you're just putting a few extra electrons in the structure, a small percentage of silicon replaced with arsenic, but the arsenic has more electrons, and those extra electrons end up arranging themselves really close to the conduction band, and that lowers the effective band gap of the structure and allows it to conduct electricity better. And then the other type, the opposite, is called p-type. This is where you're going to dope with an element that has fewer valence electrons. So an example of this using silicon again would be boron-doped silicon. And so in boron-doped silicon, going back to the periodic table, silicon again has 4 valence electrons, and now we're going to dope it with something that has fewer than that, which would be boron, which only has 3 valence electrons. So we're taking out some of the valence electrons by replacing some of the silicon with boron. And so the result of that is that we would have our valence band and our conduction band. So valence band, conduction band, as we normally do. But then what happens in the valence band is we've removed some valence electrons because we've replaced silicon, which has 4, with boron, which only has 3. So we've taken out some valence electrons from the valence band, and that leaves some holes or positive charges in the valence band. In other words, we have some empty spots in our valence band that are no longer filled. So when you do p-type doping, your valence band is no longer completely filled because you've taken out some of the valence electrons, and so you have these positive charges, or what we call holes in this terminology. And so by having these empty spaces in the valence band, you have places for the valence band electrons to easily hop into, and that again increases the conductivity because there's places for those electrons to hop to that are very energetically accessible, as opposed to having to hop this large gap between the valence band and the conduction band. Okay, so those are 2 ways of improving or changing the conductivity of a material. It's called doping, and it can be either N-type or P-type. And again, that's sort of the level that we would expect you to know it as. Okay, so any questions on band diagrams? Yeah.
So the holes are just, or the dots are just holes?
Yeah, so the dots are holes. They're basically like empty orbitals that you've introduced by virtue of taking out some of the electrons. So in a normal semiconductor, an intrinsic semiconductor like up here, the valence band is completely filled, and these little dots indicate that it's partially empty now because you've taken out some of the valence electrons. And so now that you have empty spots in the valence band, you have basically empty orbitals that electrons can hop into that are easy to get to, and that's why the conductivity increases. Anything else? Yeah, in the back. You can dope a lot of different materials. It's most commonly done in semiconductors because it has, in that case, it has a big effect on the conductivity. And also there's some chemistry behind like which materials you can and cannot dope anyway, and which we're not going to get into. So it, in principle, can be done with any material, doping, and it's kind of like, you've probably heard of alloys too. An alloy is kind of like a doped metal, though usually in an alloy it's a pretty big ratio of the two. It's not just like a tiny amount that you're doping in, but there is doping in other types of materials as well, but we're only going to talk about it in the context of semiconductors for this class. All right, anything else? All right, the next type we're going to talk about, which is still a network solid, is called a network covalent compound. So the types we talked about before this were called network atomic solids. They just have a single element in the structure. But then network covalent compounds are compounds that have 2 or more different elements and that still form these sort of covalent large networks. So as an example, let's talk about CO2 here. So we talked about CO2 a lot in this course in the context of molecular structure, polarity, a little bit about bonding. And so the structure of CO2 is a linear molecule like this, and it has 2 sigma and 2 pi bonds. And it's a nonpolar gas. Now, if we go to SiO2, so as we said, silicon is right below carbon. So you might think like, oh, SiO2 might have the same structure because silicon also has 4 valence electrons. It can form the same type of molecule. But SiO2, which you guys know more commonly as sand, is clearly a lot different than CO2. There's different types of sand, but SiO2 is one of the major components in sand. And it's quite a bit different, right? It's a hard solid. It's a white solid. It's not a gas anymore. So why is this the case? Well, the difference is that when we go from carbon to silicon, carbon we're using 2p orbitals, and they're going to overlap with oxygen 2p orbitals to make the pi bonds, and hybridized orbitals will make the sigma bonds. But in silicon, we have to use 3p valence orbitals. And it turns out something we haven't really talked about a lot in this course, but is important for this little description here, is that 3p orbitals tend to form much weaker pi bonds. All right, so we can form pretty strong pi bonds when we're using 2p orbitals on carbon overlapping with 2p orbitals on oxygen. But if we try to make pi bonds in SiO2 between silicon and oxygen, those end up being pretty weak. And that's in part because there's an energetic mismatch between the 3p orbitals on silicon and the 3p orbitals on carbon, which are much lower in energy. And so because those orbitals are far apart in energy, they don't overlap very well, and they don't form very strong bonds. So it's actually more favorable with silicon to form 4 sigma bonds instead.
Why does Si have like 3p orbitals?
Because of where it is on the periodic table. So if you have carbon here, it's in the second row of the periodic table, so it has 2p valence orbitals. Silicon is below that in the third row, so its valence orbitals would be 3p instead. And with those 3p orbitals, the pi bonds are much weaker, and so it's actually more favorable to form 4 sigma bonds instead. But if the... Good idea. Final exam's coming up. I recommend that for everybody. All right, so then we have SiO2 is 4 sigma bonds instead. Now, obviously, if it's just a single molecule, silicon and 2 oxygens, it can't do that. So what it does is it forms a network of a sigma bonded network that goes on in all directions. So I'm just going to draw a small piece of it. Basically, each silicon is now going to be tetrahedral. It's going to be bonded to 4 oxygens. And then each oxygen is going to be bonded to more silicons. And then this silicon would be also tetrahedral.
What's fun?
No. So,
That looks very...
So again, I'm not drawing the exact structure, I'm just drawing a small piece of it. But what you have are these sp3 tetrahedrally bonded silicon atoms that are going on and on in all directions. And so it forms an extended solid with very strong bonds and ends up having very different properties as a result. And so it just goes on and on forever. I'm not drawing a very big piece of it. So what you have are these SiO4 2- tetrahedra that extend infinitely. And of course, at the end of the structure, you have to cap it with something. So usually silica is going to be capped with, hydrogen or something at the end, because it's not going to be overall negatively charged. So at the very end of the structure, you'll have, like OH bonds, or you can functionalize this in different ways, but it's going to stop somewhere. But throughout the bulk of the structure, you're going to just have these SiO4 units bonding together in all directions, forming a big network. And so as we've already kind of mentioned, then the properties of this are very different than CO2. It's no longer a nonpolar gas, but it's a hard, brittle solid. So it's hard, meaning that it's not easy to sort of deform it, but it's brittle, meaning that if you try to deform it, it's going to just shatter into pieces. So it's a hard, brittle solid. And examples of network covalent compounds are sand, which is SiO2 is a major component of that. And then glass also contains SiO2. It's in an amorphous form, so it doesn't have a regular structure, but it's going to, again, be this sort of network structure with silicon-oxygen bonding going on in all directions. So that's the other major type of network solid, is a network covalent compound. And this is really the only one we're going to talk about. So our entire discussion of network covalent compounds more or less fits on this one slide here. Okay? So then what we're going to do now, before we move into the last type, I guess I could have put this at the end, but it's fine to do it now. Let's talk about the different types of solids that we have now classified. We're still going to have to talk in detail about the last one that we haven't gotten to yet, but let's go through a summary now of what we've done so far and then what's coming here for the last little bit. All right, so the first classification we talked about was a metallic solid. Now again, with solids, we also have the structural classification that we talked about, crystalline versus non-crystalline. And that's determined again by whether the atoms are regularly ordered or sort of just randomly ordered. But these are sort of the chemical classifications of solids, the different types of solids that we talked about from a chemistry standpoint. And so in a metallic solid, the lattice points in the structure are going to be just the metal atoms. So we talked about the structures of those and how the lattice points are occupied by metal atoms, and they arrange themselves in different ways, layer themselves in different ways to form different structure types. And an important thing to be able to do is to be able to classify a substance into one of these structure types. And so if you want to identify something as a metallic solid, of course, the formula is just going to be one type of metal atom in the formula. So basically any metal element would form a metallic solid in its solid form. All right? So, all kinds of elements, there's, probably at least 80 elements on the periodic table that are classified as metals. All of those would form metallic solids when they're in their solid state. The forces that hold these together, so in all these different solids, you have forces holding together the different components in the structure. So in a metallic solid, you have metallic bonds that we talked about, which again, we sort of classified as a sea of electrons, those delocalized electrons that float around the structure and hold everything together. That's the metallic bonding that holds these structures in place. And again, many examples of these that are very common. So pretty much any element on the periodic table that's a metal would fall under this category here. Sodium, iron, lead, etc. Any metal on the periodic table would be classified as a metallic solid when it's in its solid form. The type that we just finished talking about is called a network covalent solid, which, as we said, has sort of two sub-classifications: network atomic solids, which are elements, or network covalent compounds, which have two or more different elements in the structure, but again, there's sort of a lot of similarities between them. In this case, the lattice points in the structure, the components that make it up, are non-metal atoms. So that's the sort of easier way to recognize a network covalent solid versus a metallic solid is what is it?
Covalent solid?
Network covalent solid?
Yeah.
And so then, the requirements for forming a network covalent solid is that you have only nonmetals in the formula. And some of the metalloids would also fall into this category as well, like silicon we talked about is a network solid, kind of in between a metal and nonmetal, but it would still be classified in this way. So it can have one or two nonmetals in the formula, possibly more than two, but the types we talked about today were just a single element, which was a network atomic solid like carbon, or two elements like SiO2 that make a network covalent compound that has two different elements in it. And the forces that hold them together are the covalent bonds between the atoms. All right, so because these are made up of nonmetals, the atoms are going to be bonded to each other covalently, and that's what holds the whole structure together. And then examples of this we talked about already today would be graphite, diamond, silicon, other semiconductors like germanium, or SiO2, which we talked about as a network covalent compound. So those non-metal and metalloid elements that form these extended structure types would be classified as network covalent solids. And then there's two more types that we need to talk about. One of them we're not going to really have any slides on because there's not too much to say about it. But one that we're going to see and be able to classify are called molecular solids.
What does the answer SI?
SiO2.
Wait, no, I'm talking about like the...
GE, germanium.
Oh, yeah.
Yeah. All right, so graphite, diamond, silicon, germanium, SiO2 are classic examples of network covalent solids. Another type that we haven't introduced yet, and I'm really going to only do in this summary here because there's just not a lot to say about it, are molecular solids. So in this case, a molecular solid is a molecular compound, so like for example water, and it's now in its solid state. So water, when you cool it down to ice, would be an example of a molecular solid. It's a solid made up of molecules. Or dry ice, CO2, is an example of a molecular solid. Or the one element that would fall into this category would be iodine, I2, or P4 phosphorus, or S8 sulfur, all these elements that are solid but made up of molecules, and that would be called a molecular solid. So in this case, the lattice components, we're not going to talk about the structures of these in very much detail at all, but they're going to be made up of discrete molecules. And again, they can be amorphous or crystalline, but basically what you have are molecules that are sort of packed together into infinite arrays to make up these solid structures. And again, the requirements for these are that they are made up only of nonmetals, but in this case, they're going to be nonmetals that either in their elemental form or in a compound form molecules, not extended structures. So basically, most other, nonmetals besides the few that I've listed here, most other nonmetal compounds or most other nonmetal elements would fall into this category if they're molecular. And so the forces for these would be, you have the individual molecules that are held together by bonds, of course, but the forces that hold them together in the solid are just going to be the intermolecular forces between the molecules. So example, when you have water that freezes into ice, you have H2O molecules, and those molecules are going to be held together into a regular lattice by hydrogen bonding primarily between the oxygen and hydrogens in the adjacent molecules. So you're going to have, hydrogen bonding, dipole-dipole forces, or dispersion forces. Again, which of these you have depends on the type of molecule that's making up this solid. So it can be any combination of these three, depending on what the structure is. So for a nonpolar, substance like iodine, I2, in the solid form, the only intermolecular forces holding those iodine molecules together are the dispersion forces because it's nonpolar. But it's going to be those IMFs that hold it together in its solid state. And so examples are, again, a lot of non-metal elements that would form solids that are molecular in nature. So I2, P4, S8, ice, solid CO2, dry ice. So basically any covalent compound or any covalent element, any molecular element, once it's in a solid form, would be classified as a molecular solid. And again, the key there is that the only force holding the molecules together in the solid are the intermolecular forces between the individual molecules. All right, and then the last type that we have to talk about today, we're going to get into more details of the structures of these here in a little bit, are ionic solids. Now for us, recognizing ionic solids is very easy because any ionic compound in its solid form is an ionic solid. We know how to identify ionic compounds from stuff we did a long time ago. And so the components in this, as we'll talk about, are ions. So the different ions in the structure, positive and negative, sort of arrange themselves into a regular structure. That's going to make up that lattice or that crystal structure that forms these types of solids. And the requirements are, the formula of these are going to be a metal and a nonmetal together. We've already talked about that at length back in chapter 3 when we first introduced ionic compounds. So an ionic compound has a metal cation and a nonmetal anion paired together, and they're held together by those ionic bonds, those strong forces of attraction between the oppositely charged ions. And there's tons of examples, but again, any combination of metal and nonmetal. So sodium chloride, magnesium oxide, magnesium chloride, all kinds of examples of, these are binary ionic compounds, which are the types that we'll talk about in terms of their structure. Okay, so those are ionic solids, and that's the last type that we're going to cover then in this last part of today's class if we have time to get through all of it. All right, so that's the classification. So make sure you know how to do that. Make sure if we give you some substances, you should be able to classify which type of solid they form, again, based on primarily the chemical formula, and then know some things about how they're held together and so on. Okay, so let's talk about ionic solids last. And so when we're defining the structures of ionic compounds, as we've already talked about at length in chapter 3, the ions are held in place by forces of attraction. So when you have these regular structures where the ions are arranged in these repeating patterns, they're held in those positions by the virtue of the fact that they have those strong ionic forces, ionic bonds between the neighboring ions in the structure. So the ions are held in place by forces of attraction between the oppositely charged ions. All right, so that should not be breaking news to us because we already have a pretty good idea of how ionic bonding works based on what we talked about before. And the way that they arrange themselves, though, so how do we, how do the ions decide? I mean, they're not sentient beings, of course, but how do they, how is it determined how they arrange themselves or what kind of structure they make? Well, that's going to be primarily determined by the arrangement that maximizes those attractive interactions. So that's really what, all chemical species want to do. All chemical substances, they want to maximize attractive forces and minimize repulsive forces. So you have attractions between oppositely charged ions, but you also have repulsions between the ions that are the same charge, and they're going to arrange themselves in a way that the attractions are maximized and the repulsions are minimized. All right, so that's how it's going to work. That's why we get these different structures. And so the way that these structures form is we're going to think about sort of the two ions separately that make them up. Typically one of the ions is going to be larger than the other. I suppose they could be close to the same size in some cases, but one's going to be larger, one's going to be smaller. As we talked about also before, the larger ion is usually the negatively charged ion, because when we add electrons to something, it gets bigger. When we take electrons away, it gets smaller. So in most ionic compounds, the anions are the bigger of the two ions, but either way, you're going to have one that's bigger, one that's smaller. And so those larger ions are going to occupy one of the common packing arrangements that we've already talked about for metals. And usually it's going to be one of these three. We'll talk about the first two, of course, at more detail. So primitive cubic or face-centered cubic. And there are, of course, hexagonal ionic compounds as well, but we're not going to get into those structures in this course. But the larger ions, usually the anions, are going to arrange themselves in one of those arrangements, either primitive cubic or face-centered cubic. And then as we talked about, in those structures, you have gaps in the structures. The packing efficiency is not 100%, so you have little gaps in the structure, and the other ion, the smaller ion, is going to force its way into those gaps in the structure, and that's where it's going to reside. So again, the smaller ions are usually the positive ones, because those are the ones that we've removed electrons from, and they're going to occupy holes in the structure. All right. So the observed structure that we get and which holes are going to be occupied depend on the relative sizes of the ions. So there's basically different types of gaps that positive ion can force its way into in the structure, and which of those gaps it goes into is going to depend on how big that positive ion is relative to the negative ion that's occupying the other position. So we'll talk about that and how it depends again on how the comparative sizes of the two. All right, so let's talk about the different types of holes that we have in the structure. So the first of these are going to involve the face-centered cubic structure. And so the way that the first type we're going to talk about are tetrahedral holes, which, as the name suggests, is going to be a tetrahedral arrangement of one ion that's going to be then another one forcing its way into that gap. So these are going to occur in the cubic close-packed structures, the face-centered cubic structure, and these tetrahedral holes are located in a dimple in the structure. That sort of, again, is between four adjacent ions in the structure. Now, it's probably more helpful to think about where do those arrange themselves in the actual cubic lattice, not in terms of how they are in terms of the layers. So there's going to be one in each corner of the FCC structure. Remember, CCP and FCC kind of mean the same thing. So each corner region of this face-centered cubic structure is going to have one of these holes. So what we look at here, this is a face-centered cubic structure. The spheres here represent the positions on the face-centered cubic lattice that would be occupied by the anions. One in each corner, one in each face. And the purple ones are the same thing, but they're just highlighting where a tetrahedral hole will be located. So if you look at two adjacent atoms on the face, and then two adjacent corners, or sorry, three adjacent atoms on a face and one in the corner. So that face there, that face there, that face there, and that one. Those make a tetrahedron, and this X here, right at the middle of that, that's the location of the tetrahedral hole. And so there's going to be one of those tetrahedral holes in each of the 8 corners of the cube. So one down here, one in the back, here, 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 and here. So each corner is going to have a tetrahedral hole that involves the corner atom and the 3 closest face atoms forming a tetrahedron around that. So the positive ions, when they go in the tetrahedral holes, are going to be arranged in these corners here. Now let's talk about the relative size of the tetrahedral hole. So what we talked about last time is the dimensions of these structures. So in a face-centered cubic lattice, the side length A was 2 times the square root of 2 times r. And here we're going to use capital R as the radius of the larger ion, which occupies the face-centered cubic positions. And again, this derivation is not terribly important. It's just to tell you where these numbers come from, that I'm not just pulling them out of thin air. So then what we can do here is, if we go through the diagonal of the cube, let's go through half of a cube diagonal here. So as we go through one half of a cube diagonal, we're going to start here at that corner, and we're going to go through the diagonal, and we're going to end up right in the center of the cube. So that's one half of a cube diagonal. All right, so one half of the cube diagonal is equal to a radical 3 over 2. And as we set up here, a is equal to 2 times the square root of 2 times r. So we're just making a substitution there. And then as we travel through that diagonal, we're going through the radius of the larger atom, which is r. We're going through 2 times the radius of the smaller atom that resides in that tetrahedral hole. And then we're going through, again, another radius of the larger atom to get to the center here. So that's going to be equal to 2 times the big radius plus 2 times the small radius. And then so we can solve for the small radius r in terms of the bigger radius, capital R, which is going to be radical 3, radical 2 over 2 times big R minus r. So we're just doing a bunch of algebra here where we're, again, defining the diagonal of the cube in terms of the side length A in terms of the radius of the ion that's at each corner, and then the small radius being the radius of the tetrahedral hole. And so what this ends up being is the radius of the small hole, the tetrahedral hole, is radical 2 times radical 3 over 2 minus 1 times r. But the important thing for you guys to know is that this is equal to 0.225 times capital R. So that's the smallest size of a cation that you can fit into that hole. That's the size of that hole relative to the big ion. So it has to be a much smaller ion to be able to fit into that hole there in the structure compared to the size of the ions that are at the corner positions. All right, so that's the relative sizes then of those two. And as we'll see, there's going to be sort of a range of values that they can occupy. So in a tetrahedral hole, that's the size of the cation that you can fit in there. Let's do the same thing for what's called an octahedral hole. So in an octahedral hole, you would have, they're going to be in a sort of a layer context. They're going to be between 2 sets of 3 spheres in adjacent layers. But again, it's not so helpful to think about where those are in terms of the layers. It's helpful to think about where they are in the cubic unit cell. And so in the cubic unit cell, there's going to be one on each side of the unit cell, or one on each edge, I should say. and 1 in the center. So these little circles here, so again, the red spheres here are showing the face-centered cubic structure, which will be the arrangement of the anions, and then the little circles here that are smaller, that are shown in black with a little O in them indicating octahedral, those show the location of the octahedral holes. So there's an octahedral hole on each edge of the unit cell, and there's also one straight here in the middle, right at the body center. So that's where the octahedral holes are located. And again, to determine the relative size, the side length in a face-centered cubic structure is 2 radical 2 times big R, which is the radius of the anion. And then as we go through the length of a side here, so as we go through one side of the unit cell, we're going through the radius of the big ion, we're going through 2 times the radius of the small ion, that would be in the octahedral hole, and then 1 more radius for the big ion. So in this case, the side length A is equal to 2 times R plus 2 times R, where R is the radius of the anion and little r is the radius of the cation. And so again, we just have to solve for the relative values of those. So radical 2 times capital R is equal to big R plus little r. And again, what we're going to do is solve for small r, which is going to be radical 2 minus 1 times capital R, which comes out to 0.414 r. All right, so the octahedral hole is larger than the tetrahedral hole. So if the cation is too big to fit itself into the tetrahedral holes are much smaller, then the cation can instead force itself into the octahedral hole, which is a bigger volume of space for it to occupy. So that's really what we're getting at here. We're doing some derivations here just to help you see where these come from. But essentially, these different holes in the structure have different sizes, and depending on how big the cation is that's going to be in that hole, it's going to occupy whichever hole it fits in best. So for octahedral holes, they're a little bit bigger than the tetrahedral holes. Okay, so that's and then the last type we'll talk about is the simplest of the three, at least in terms of visualizing it, which is a cubic hole. So in a cubic hole, the anions are no longer face-centered cubic, they're just going to be a simple cubic arrangement, and the cubic hole is just going to be right at the center of that simple cube. So it's very easy here. So it's going to be the center of a simple cubic arrangement. We're talking about the cubic hole. All right, center of a simple cubic structure is called the cubic hole. So this is sort of, again, a space-filling diagram, which shows the light gray atoms are the anions, and you're forcing a cation right there into the middle of those on the corners, or here shows some space in between them, where again, the anions are located on the corners of the cube, and you're forcing the cation right into the center of that. So it's a simple cubic structure with just the opposite charged cation forced into the middle. So in this case, the relative size we can determine in this way. So in a simple cubic structure, the side length A is equal to 2 times the radius of the anion that's at the corner. It's a simpler relationship. And then again, the cube diagonal here, as we go from one corner to the opposite corner through the center, as for example, that diagonal there is equal to A radical 3, which is equal to 2 times the radius of the anion plus 2 times the radius of the cation. So as we go from corner to corner, we go through 2 radiuses of the anion, and we go through the whole diameter of the cation that's at the center. So that's the relationship we have there. So we replace A with 2r, so 2r radical 3 is equal to 2 times big R plus 2 times little r. Simplify, r radical 3 equals to r plus r, and then we solve for small r, which is the radius of the octahedral hole. It's going to be square root of 3 minus 1 times big R, which is 0.732 times big R. So again, this is the largest hole yet. So we have 3 types of holes that we can force cations into, and again, depending on how big the cation is relative to the anion, that's going to determine which of those holes it occupies. So the cubic hole is the biggest hole, so if the cation is too big for the tetrahedral hole, too big for the octahedral hole, it can instead put its way into the cubic hole right at the center of a simple cubic structure. So there's these different possibilities. Again, they all depend on the relative sizes of the anions and cations. The next thing we have to be able to do is count the holes. How many of them are there in a structure? So for the tetrahedral holes, again, this is FCC, and we said in the face-centered cubic lattice we'd have 4 anions if we're occupying the face-centered cubic positions with anions, which are shown in red here. Now, how many tetrahedral holes are there? Well, all 8 of the tetrahedral holes are completely inside the unit cell. Remember that these are located in the corners, but they're completely inside the cube. They're not on the boundary of the cube, they're not on the edge or the face or anything like that. They're completely inside the cube. So all 8 tetrahedral holes are inside the unit cell. And so because we don't share those with other neighboring unit cells, those each count as a full ion in the structure, in the unit cell. So in total, there's 8 tetrahedral holes. And so if you have 4 anions in the structure, you can put up to 8 cations. Now you're only going to fill however many tetrahedral holes you need to balance the charge. You won't always fill all of them, but there's a possibility of putting 8 cations into those 8 tetrahedral hole positions in these structures. And we'll give examples to see how that works in a little bit. For the octahedral holes, we said that those are located on the edges of the cube as well as one directly in the center. All right, so to count the octahedral holes, again, we're talking about a face-centered cubic lattice, so there's going to be 4 anions in the structure for face-centered cubic, and then how many octahedral holes would there be? So to count that, we have all 12 edges of the cube are occupied by an octahedral hole. 4 on the top, 4 on the bottom, 4 along the sides. So there's 12 edges in a cube, and each of those is going to count as 1/4 because each edge in a cube is shared by 4 neighboring cubes once we stack them together into a larger structure. So we talked about that last time, how to count the different positions. Edges count as 1/4 each. And then there's one directly at the center that's not going to be shared, so that counts as a whole ion or a whole tetrahedral or an entire hole, and that's going to be a total of 4 octahedral holes. All right, so there's a 1-to-1 ratio between the anions and the octahedral holes in the structure when you're filling the octahedral holes. And then finally, for the cubic holes, we have simple cubic arrangement of the anions. So that's just going to be in that 1 anion in the structure, because there's 8 corners, each counting as an 1/8. But then for the cubic hole, we have 1 at the center. It's unshared, so it's going to count as a full unit, and that's going to be just 1 cubic hole. So again, the ratio is going to be 1-to-1 for the anions versus the cubic holes. Now, as I said, how many of these are filled are going to depend on the formula of the compound, which is depending on the charge of the ions involved. But you're going to fill up to 8 tetrahedral holes, 4 octahedral holes, and 1 cubic hole in these structures. And we'll, again, see some examples of how that works then. All right, so to summarize then, the most important information to know about these different types of holes is, again, what we just went through already, so we'll just summarize it here in more concise form. So the number per unit cell we just determined was 8 for tetrahedral holes, 4 for octahedral holes, and 1 for cubic holes. Again, that's going to help determine the formula of the compound once we start filling those holes. And then we also talked about the relative sizes. So how big does the smaller ion have to be able to fit in one of these holes? So it turns out what happened is we saw that the radius that we calculated for tetrahedral hole was 0.225 times the big radius. And the radius we calculated for tetrahedral hole was 0.414. And the radius for cubic hole was 0.732. Now what actually happens though is there's going to be a range of values within these. So in the tetrahedral hole, this is going to be the size of the hole when the anions are completely touching each other. But in reality, the cation can sort of force its way into that hole and kind of expand the structure a little bit. So it's going to basically force its way into the gap and sort of spread out those anions a little bit and make the hole a little bit bigger. So you're going to find a range of values. So the tetrahedral hole is going to be occupied typically when the radius goes from this value here, 0.225 times the big radius, up to the size of the octahedral hole, which is 0.414. And then if the cation is bigger than that, if the cation radius is more than 0.414 times the anion radius, if the relative sizes is bigger than that, then you'll start filling the octahedral holes up again and those are going to fill, and you can expand the structure a little bit until you get to 0.732. And then at that level, it's going to be favorable to fill the cubic holes, and the cubic holes will be filled anytime the relative size of the smaller ion is more than 0.732 times the size of the larger ion. So there's always going to be a range of values that are possible. So you're not going to usually have exactly 0.225 or exactly 0.414, but if it's anywhere in that region, you can fill the tetrahedral holes. If it's anywhere in this region, you can fill octahedral holes. And if it's bigger than 0.732 in relative sense, then you'll start filling the cubic holes. So there's always a range of values. And again, it's also important to realize what is the unit cell for the larger ion that gives rise to these holes. Tetrahedral holes and octahedral holes both occur in a face-centered cubic unit cell, whereas the cubic hole occurs in a primitive or simple cubic cell. So there's different unit cells for the anions that are possible as well. All right, but those three types of holes and those two types of cubic structures that we have can basically allow us to summarize the structures of a lot of different ionic compounds. Okay? All right, so let's go on and then talk about some examples of ionic structures to see this in practice. So as we said, ionic solids are created by filling holes in the structure with the opposite ion. So let's talk about sodium chloride, NaCl. So the ionic radii of sodium and chloride, these again are not numbers that you have to memorize, but I'm going to give them to you here. It's 102 picometers for sodium plus, and for Cl minus, it's 181, sorry. All right, so as we said, the anions are usually larger, and that's because we're adding electrons to the anions, which expands the radius. 102 picometers? What is that? That's the radius of the sodium ion. And the radius of the chloride ion is 181. So which structure they're going to form when they form sodium chloride, again, depends on the relative sizes of the anions and cations. That's why we have to know those values. All right, so if we look at the radius of those, again, the chloride is larger, so that's going to occupy the main lattice positions, and the sodium will fit into some of the holes in the structure. So if we take the radius ratio of those two, sodium plus to Cl minus, it comes out to 0.56. And as we said, if it's between 0.414 and 0.0732, that's when we're going to start filling the octahedral holes. So if we were going to predict the structure of sodium chloride, which is actually what is observed, we would expect that based on this relative ratio of 0.56, that's between the limits of the octahedral hole. So we're going to put the chloride ions on the face-centered cubic position. That's going to be shown in green here. And then we're going to fit the sodium ion, shown in orange, into the octahedral holes, which are along each edge in the center. All right? So how many of those holes are going to be filled, though? We have to make sure we're filling the right number so that the formula of the compound is correct. So in a face-centered cubic lattice, the chloride ions are going to be in the face-centered cubic positions. And as we said, there's 8 corners and 6 faces. So a total of 4 chloride ions in the structure when they occupy the face-centered cubic position. And then we need to have also 4 sodium ions to balance the charges. So as we talked about for the octahedral holes just a little bit ago, 12 of those are on the edges. 1 is in the center, so there's going to be 4 octahedral holes, so we need to fill all 4 of them. All right, if we filled only some of the octahedral holes, we wouldn't have the charge balance. We need to fill all of the octahedral holes to make sure we have the same number of cations and anions in the unit cell, such that the charge is balanced, because there's a +1 cation with a -1 anion. So we're going to fill all of them. So in reality, the formula for one unit cell is Na4Cl4. There's 4 cations and 4 anions in each unit cell, but of course the simpler form of that, which is how we'd write the formula, is just NaCl. So there needs to be a 1-to-1 ratio of cations and anions in the structure because of the charges. Now the other thing we can talk about is the coordination number, which we haven't really mentioned yet. But for an octahedral hole, the name kind of gives it away. In chapter 4, we learned that octahedral is a structure that has 6 things bonded to it. And that's going to be also true for the octahedral hole. So if we look at this center atom here, we have 1, 2, 3, 4, 5, 6 anions surrounding it. So the coordination number for an octahedral hole would be 6. Again, the name kind of gives that away. We learned octahedral is 6 things bonded to it before, and that's going to be true for this as well. That's why we call it an octahedral hole. So again, focusing on that one in the center tells us that. So that's some aspects of the sodium chloride structure. Let's just do a few more until we run out of time. So the next one here is going to be cesium chloride. So sodium chloride and cesium chloride are both similar. They both have an alkali metal cation, and chloride is the anion, 1-to-1 ionic compounds. But then let's look at how the structure can be different for these because of the sizes of the ions involved. So in this case, we have cesium and chloride, and it turns out that the radius of the cesium ion is actually pretty similar to sodium, or similar to chloride, I should say. Only a little bit smaller. So the cation is still a little bit smaller than the anion, which is usually the case, but in this case they're much closer to each other. And so when we take the ratio of those two, cesium plus over Cl minus, again, we're using little r for the cation, big R for the anion, but it's just the radius of each one. 174 divided by 181 is 0.96. And as we said, if the cation radius is more than 0.732 times the anion radius, we have to start filling cubic holes instead. They're too big for the octahedral holes and way too big for the tetrahedral holes. So when the radius are this similar to each other, we have to fill the cubic holes, and that's what we do in cesium chloride. So we're going to form a simple cubic arrangement of the chloride ions at one at each corner. And so how many of each are there? 8 corners, counting as an eighth. So there's one anion, one Cl minus, and then for the cubic holes, there's one at the center that counts as a full unit because it's in the middle of the unit cell, not shared, and so that counts also as one. So they're going to be one of each. So in the cesium chloride structure, we just fill every single cubic hole with the cesium atoms. We have 8 chlorides in a cube, cesium sort of forced into the center, into that cubic hole there, and that gives you a direct 1-to-1 ratio. The coordination number for a cubic hole, just like we have in the body-centered cubic structure, the cubic hole is right at the middle, is bounded by all 8 of the corner atoms, 1, 2, 3, 4 on the top, 4 on the bottom. So the coordination number for a cubic hole would be 8. All right, so we didn't talk about coordination numbers yet for these different holes, but they also can be defined as well. It's going to be 8 for a cubic hole, where that 1 in the center is neighboring all 8 of the corners. All right, so any questions on that? Okay, let's see. All right, one more and then a couple sample problems. We probably won't get to the sample problems. I might just do them at the beginning of next time, but let's talk about one last structure here. Shoot. All right, last one we'll talk about is zinc sulfide. Okay, so zinc is going to be a 2+ cation, sulfide is a -2 anion, so we would predict that the formula of this should be ZnS, one of each cation and anion. And if we look at the radii this time, zinc is 2+, so because it has a 2+ charge, it has a really small radius, 60, and then sulfur 2- is similar to chloride, it's on the same row of the periodic table, so it has a similar radius of 184, okay? So those are the 2 radii this time for the cation and the anion. And again, to predict which holes are going to be filled, we have to look at the relative ratio, the relative radii of those two, the ratio of them. So we take the smaller, which is the cation, divided by the larger, which is the anion. And that's going to be 60 divided by 184, which is about 0.33. Okay? And as we said, if the smaller radius is between 0.225 and 0.414 times the biggest radius, those are going to go into the tetrahedral holes. All right? So when your cations are really small relative to the anions as they are here, then they can fit into those smaller tetrahedral holes. That's what we're going to do here. Now the question is, though, do we need to fill all the tetrahedral holes or just some of them? So again, for that we have to look at how many tetrahedral holes are there and how many of each ion do we need to be able to balance the charge. So for the face-centered cubic structure, which is what we're going to have to occupy to make tetrahedral holes, so the sulfides, which are shown in yellow here, are going to be at the face-centered cubic positions, and there's going to be 4 of them. We counted those earlier, so I'm not going to go through the counting again, but in a face-centered cubic lattice, there's 4 atoms per unit cell. And then when we counted the tetrahedral holes earlier, we saw that there was 8 of them, and they're all inside of the unit cell, so there'd be a total of 8. So in this case, though, we need equal numbers of cations and anions. So if we filled all the tetrahedral holes, we'd have 8 cations and only 4 anions, but they need to be the same. So for this structure here, we're only going to fill half of the tetrahedral holes. So it is very much possible in some of these structures that you don't fill every single hole. You just fill the number that you need to fill to be able to balance the charge. So if we have 4 anions, we also need 4 cations, but there's a total of 8 tetrahedral holes, meaning only half of them need to be occupied in this structure. And that's what's shown here. So we have 4 of those zinc atoms shown in purple here in the tetrahedral holes near each corner, but then the other 4 corners are not occupied at all. They're empty. Okay, so that's what the zinc sulfide structure looks like. Half of the tetrahedral holes are filled to make sure that we maintain charge balance. And then for the coordination number again, the name of the hole gives it away, so this should not be anything surprising. We learned back in chapter 4, tetrahedral means it's bonded to 4 things, so the coordination number for a tetrahedral hole would be 4. And we can see that here. So this zinc atom in purple has 1, 2, 3, 4 sulfur atoms that are surrounding it in that tetrahedral hole. All right, I think I'll stop there since we're out of time. So I'll do these last 2 sample problems at the beginning of next time. We'll just do that before we start the final exam review. That should be fine. So I'll put those, I guess I'll just put those at the beginning of the review so you don't have to print out 2 different things, or if you already have this, just bring it back with you. So we'll finish off these sample problems. I encourage you to do them on your own if you want to try them, but I'll go over them quickly at the beginning of next time, and then we'll be ready to start the final exam review right after that. All right, so I'll be in my office for a lot of the afternoon today, so if you, or from now until at least probably 2:30 or 3, so if you need to come find me, I'll be there, and help get ready for the exam next week.